Okay, good. Well, I'm really pleased to be back here, and hopefully you're all awake. I'm not sure I am. So let me start off. Any questions from yesterday? Anything you like? There are a couple things that several people asked me, which I do want to clear up at the beginning. But any other questions that people have from what I did? Okay, well let me say a couple of things. Are there lights here? No, I guess it's dark. Okay, so let me say a couple of things. So the first thing is, what we did was introduced what pseudodifferential operators are. I talked about oscillatory integrals. I talked about all the various properties of pseudodifferential operators, and I talked about, perfect, thank you. And I talked about some applications, okay? Now, one thing that I talked about was the symbol mapping, that given any pseudodifferential operator, you can associate a symbol, and vice versa. You could start with a symbol and get a pseudodifferential operator. And the point being that there's sort of a pretty good bijection between these, but modulo low order terms. And the point which I don't think I made clearly enough is that, for example, on a manifold, so on some manifold, whether compact or not, I can define this space psi star of m. So the star stands for the order of the operator. Okay, so it's filtered by the order. And these are well-defined objects, so it's not that they're only defined modulo low order terms. So here's my manifold. What is an element here? So an element is, well, if I take any open cover, so I have an open cover of the manifold, it says that, if I have this mapping down to some, V sub alpha down here with the diffeomorphism F sub alpha, that if I take my operator here, move it to an operator here using a diffeomorphism, so I take, whichever I'm going to call it, A sub alpha is the local representation by sort of conjugating by this diffeomorphism. This is a pseudodifferential operator on V sub alpha. And similarly, if I take it to some V sub alpha primed, also an Rn, so this is some F sub alpha primed, I get another operator, A sub alpha primed, and these are related by this overlap diffeomorphism. So it's just the usual thing with coordinate charts, right? So I have something that if I pull it down to any coordinate chart, it becomes a pseudodifferential operator in this sense in Euclidean coordinates. And that's a coordinate invariant thing, okay? So namely, having a pseudodifferential operator here, I pull it over here, I still get a pseudodifferential operator. So that's perfectly well-defined. Now, the thing that's not well-defined is the full symbol. I can take the symbol of it, and it's only defined modulo low-order terms, right? So given A sub alpha, I can talk about the symbol, whatever the order is, of A sub alpha, and this is only well-defined, modulo modulo S sub n minus 1. So that's the defining as I was talking about. And similarly, if I start with a symbol down here, an nth order symbol down here, I can lift it to an operator here and pull it to an operator here, right? And of course, I've made a lot of choices in doing so, and the ambiguity is an operator of one low order. Okay, so what's well defined is this mapping from psi sub m mod psi sub m minus 1 to S sub m mod S sub m minus 1, and that's an isomorphism. Okay, and remember these things are smooth functions on the cotangent bundle with certain polynomial growth or decay properties as I go out the fibers. Okay, but the objects themselves are well defined. So anyway, sorry if I didn't explain that very clearly last time. Okay, the second thing which I did not say very nicely, and I even told you then that I was lying, I didn't have it right, was this proper regularization of oscillatory integrals. So suppose I have, so now this is just back on Rn. So I have some set here, and let's suppose I have a distribution. So this is an E prime of this open set. So this just means a compactly supported distribution. Okay, and so what I wanted to define was A of U. I just want to make sense of this as another distribution. Okay, and I gave you this, kind of horrible expression using what are called oscillatory integrals. So AU of Z is equal to the integral e to the I z dot zeta A of Z tilde zeta U tilde U of zeta tilde d zeta tilde and Z tilde, and I'm sorry, and I want Z minus Z tilde dot zeta. Okay, so I get d zeta. Okay, so I wanted to regularize this properly. And what I did want to say, and it's an important point, which is why I wanted to say it again, is that, of course, I'm expecting A of u to be another distribution. It's not going to be a smooth function, right? So namely, given a distribution, A of u is supposed to be another distribution of some order, okay? So how do we define a distribution? Well, we only know what happens when we pair it with a test function, right? So suppose I have a test function, so find C for d0 u. So it's a so-called test function. Right? Then the only thing that's really supposed to make sense is A of u paired with v. That's supposed to be a number, right? So that's what I have to make sense of. Okay, so in other words, the integral that I'm trying to regularize is sort of a triple integral now. And then I have this e to the I, z minus z tilde zeta. I have this a of z tilde zeta, u of z tilde, phi of z, d z tilde d zeta. Okay, so it's this thing that I need to regularize. Okay, now let me say carefully how I do it, because I said the wrong thing yesterday. Okay, so what do we know about u? So I know that u is a distribution. That means that u is in some hs for some s. Why is that? Well, because it's compactly supported, right? So I know that u hat, its Fourier transform is slowly growing. It's polynomially growing. So standard properties of the Fourier transform. And so u is in hs for some s, and it's compactly supported. So in particular, this first integral, so let me do this sort of in stages, this e to the minus I z tilde dot zeta. Now I have to include this single piece here, right? So this thing is a function of zeta and z. So let me call this is a function of, let's say, h of z, there's still a z there, and zeta, right? And what do I know about this h? Well, it's slowly growing in zeta, right? Simply because this is compactly supported. This is just multiplying by some smooth function, so that's doing something pretty harmless, right? So I integrate in z tilde, and it's like taking the Fourier transform of a compactly supported distribution. Okay, so this is slowly growing. Namely, it's growing no faster than some polynomial. But now it has, right, so it has this property, and the integral in zeta now that I have to take, that's a disaster, right? Because I have this thing that's just growing in zeta. It's a very non-convergent integral. So what I have to make sense of now is this e to the I z dot zeta, and then I'm going to have this phi of z times h of z dot zeta, d zeta dz. Okay, so that's the thing I have to regularize. Okay, so I've just taken the Fourier transform, now I have to regularize this. Okay, so now the point is the following, that if I take this e to the I z dot zeta, then I'm going to do something very similar to what I did before. So I just remember the rule. So if I take a d zeta j of this, I'm going to have a zj. If I take a d zj of this, I times zj of e to the I z dot zeta, I'm going to have an I times zeta j, e to the I z dot zeta, z dot zeta. Okay, so what I do is, sure I have the right regularization here. Yeah, okay, so I take the sum zeta j dzj plus zj d zeta j applied to this e to the I z dot zeta. So I just cook up a particular differential operator here. What does this do? So the dzj brings down to zeta j. So this is going to give me a mod zeta squared. The zj times d zeta j, so this is going to give me a zj squared. So in fact, what I want to do is I want to take a mod zeta squared times this. So this is going to give me plus mod zeta squared times mod z squared times e to the I z dot zeta. So I think I did that right. Okay, so I put in this factor of mod zeta squared here. Okay, so altogether, the differential operator I want to take L, I want to divide by this piece here, right? And notice this is a perfectly nice invertible piece now. So I'm going to have the sum zeta j dzj plus mod zeta squared zj d zeta j divided by this, well, let me write it as mod zeta squared times 1 plus mod z squared. Okay, so this is non-vanishing. Now, there's always a problem near zeta equals 0, but remember, well, maybe I'll remind you, we never care what's happening near zeta equals 0. The reason being that I can just put in a cutoff function, chi of zeta, where chi of zeta is something that's compactly supported. Excuse me, the other way around. So, sorry. Chi is the opposite of that. Right, and the reason is that I've excised something of compact support, and anytime I take the Fourier transform of something of compact support, I get something smooth. So anytime I cut away a compact piece of the zeta integral, it just gives me a smooth error. And in this game, smooth errors don't count. We only care about singularities.
So in this calculus, where is h integral?
So I haven't done this, let me return to this integral now. Okay, so I'm not there yet. So here's this L. Okay, and so L has the property that L applied to e to the I of z dot zeta is going to be essentially, so there's going to be a compact error. Let me forget about it for the purpose of notation. Is going to be e to the I of z dot zeta again. Okay. Now, what do I know about these coefficients? So here, the coefficient of d by dzj is of the order 1 over zeta, and the coefficient of d by d zeta j is of order 1. Okay. So now let's finally go back to this integral, e to the I z dot zeta, h of z zeta, phi of z, d zeta dz. Okay. Now I can put in some enormous power of L here. Right? It doesn't harm things because L of this thing gives you exactly the same thing back. Okay. So then I formally integrate by parts. So this is now a definition, if you like. I'm going to demand that this thing is equal to what I get by integrating by parts. So I'm going to have L transpose to the n acting on h of z zeta, phi of c, d zeta, dz. Okay, so in other words now, the real definition of this integral is this thing. This thing doesn't make sense because this integral is diverging, this grows slowly. This makes sense if n is very large simply because if you think about it, every time a zeta derivative hits h, remember there's a symbol there, every time a zeta derivative hits h, it gets better and better. So if I hit it with n derivatives, that's going to be decaying fast enough to be integrable. And all the z derivatives, well, they have a 1 over zeta. So if I hit it with n z derivatives, it also gives me decay in zeta. Okay, so by taking n large enough, this is a perfectly convergent double integral. Now the price I've paid, well, price, whatever you call it, is that I'm also differentiating in phi. So in other words, this is not, when I took this integral before pairing with phi, it doesn't make sense. But once I've paired with phi, it makes sense, but it relies on n derivatives of phi. So it's a distribution, it's an nth order distribution. Okay, so that's the meaning. Now, again, I say take an n large so that this is a convergent integral. Okay, so that makes perfectly good sense. I've made a choice, I've chosen n. What happens if I were to choose an n prime, some different n? Right? Well, as long as I have two different expressions with a capital N and a capital N prime, and they're both in the convergent regime, I can integrate by parts to go from one to the other. So namely, it's independent of the choice. Once I've hit it with enough derivatives to be convergent, then it doesn't matter how many derivatives I hit it with because they're all equivalent. Okay, so that's the proper definition of an oscillatory integral. Namely, I've now defined this thing, but it only makes sense as a distribution. It doesn't make sense as a function. Okay. Now, there's a caveat here. So suppose that U is actually smooth. Suppose that U is not a distribution, but suppose that U is actually a smooth compactly supported function. Okay, how does this argument change? Well, I do the same first step. So I want to look at that thing, but I look at this first step here. So if U is C infinity 0, well, then this thing is no longer slowly growing, it's rapidly decaying because I'm taking the Fourier transform of a smooth compactly supported thing. So this is already rapidly decaying, and I don't need to do any of these shenanigans. This is already smooth. And I can differentiate it with respect to, I can take that integral, I can differentiate with respect to z as many times as I want. It brings down a bunch of factors of zeta, but I have rapid decay after the z tilde integral, so that's all convergent. Okay, so in other words, just to summarize, when U is compactly supported distribution, I need to go through this whole song and dance in order to make sense of this integral. If U is a C infinity 0 function, then this first step already gives me a rapidly decaying function, and everything is convergent and smooth in Z. Okay, so that's the thing I should have said yesterday. Okay, so next step. The computation I did do yesterday tells me something, but not what I told you it does. It tells me something else. So let me rethink that, and then finally we'll get to this promised coordinate-free definition that we talked about a long time ago. So I did this all carefully because oscillatory integrals are just hopelessly confusing if you haven't seen them before. So, okay, so what I did do the other time is the following. So I wrote AU of Z in this form. So again, let me read Z minus Z tilde dot zeta. A of Z Z tilde zeta. And then I'm going to write this as, let me write this explicitly as a d zeta times U of Z tilde d Z tilde. So double integral. Namely, I want to sort of separate this out with this zeta integral done first. Okay, now I can justify that, and maybe it's a good exercise to say why I can justify that, but this is only going to be a distribution. So I'm going to call this K sub A of Z and Z tilde. So once I've sort of integrated out the zeta, I'm just left with the function of Z and Z tilde. So namely, I've written this thing as the integral K sub A of Z and Z tilde, U of Z tilde d Z tilde. And so K sub A is called the Schwartz kernel. Okay. Okay, so in other words, I'm saying any operator can be obtained. In fact, there's a great, very general theorem called the Schwartz kernel theorem that says take any linear operator whatsoever, any linear operator, right, that acts from smooth functions to distributions. So namely, I take any operator A from, let's say, smooth function from C infinity 0 to D primed. It is always represented, this is kind of the key, represented as an integral kernel. Just in the form that I've written it here. Okay. Now, if you think about this, this is saying absolutely nothing. This is one of these theorems that sort of, so what is a distribution? A distribution is a black box. It just means you feed in a test function and, right? So all this is saying is that, you know, if I have so if I have an A of U, this is supposed to be a distribution, so it makes sense when I pair it with phi. That's going to be exactly the same as the distribution K sub A, this guy acting on, excuse me, let me say it this way, the distribution K sub A acting on phi tensor U. So this is phi of Z, U of Z tilde. So this is just a restatement of this fact, right? A of U is supposed to be something whose only identity is, his only existence is what happens when I feed in a test function, right? So I can either think of it like this, which is from the original definition of A, or I can think about it like this. Right? And the reason why, I mean, the proof of the Schwartz kernel theorem is just saying that things like this are dense in the space of smooth functions on omega cross, on U cross U. Okay, so it's kind of an abstract theorem that's almost content-free.
So at this moment, there is no request on the symbol A.
Well, right now I haven't said anything about symbols. Okay, all I've said is that any operator doesn't need to be pseudodifferential. Just any weird operator you come up with is always represented by a distribution. Okay, now if we have a pseudodifferential operator, I told you it's given by this formula with this kind of justification behind it. Okay, if I rewrite it like this, there's some Schwartz kernel. And now my question is, what is special about K sub A? So namely, we're on some open set, U cross U. Here's U and U. K sub A is space, right? And if I take a general distribution, that corresponds to a general linear operator. Okay? But if I have a pseudodifferential operator, what's so special about this distribution? So that's my question. Okay, and there's an answer, which is the following. So the answer is the following, that K sub A is C infinity away from the diagonal. So we all know what that means. And here's the sentence I have to explain, and conormal with respect to the diagonal. So this is a special class of distribution. So let me just sort of say this in broader strokes. Take a product space, U cross U or M cross M. This can be on a general manifold. This doesn't need to be just an open set. Okay? I'm going to define a very special class of distributions on these things where there's a singularity exactly on the diagonal. Away from the diagonal, I'm smooth. And on the diagonal, there's some kind of mysterious property, which I'm going to tell you all about. And that's the general definition of a pseudodifferential operator. No coordinates, right? No oscillatory integrals. It just says, I have these canonical distributions. There's going to be a nice and very clean definition of these. And the operators for Schwartz kernels are these. That's what pseudodifferential operators are. And all of this sort of prologue with oscillatory integrals is a way of like doing calculations, right? But the real things are these. Okay, so that's the important point. Okay, so how do I see this? How do I justify that definition, and what is conformality? And maybe the right way to say this is that, so when I said in my abstract that, there's sort of a nice geometric theory of distributions, if I take a general distribution, it's just some horrible thing that, all I know is I plug in test functions, I get numbers, right? But what I'm saying is that there's actually nice subclasses of distributions which are associated to geometric objects, okay? And so I'm going to tell you a particularly nice subclass of distributions associated to the diagonal, which is a nice geometric object. That's a coordinate-free thing, and the Schwartz kernels, which are those types of distributions that the guys were interested in. Yeah, Stephen. Okay, yeah, so I meant to say history part 2. So let me, so history part 2 was, so all this oscillatory integral stuff happened in the early mid-60s, and then this sort of recognition that the Schwartz kernels were kind of the things you should be focusing on goes back to actually Melrose in the early 1980s, okay? And there were various reasons for doing this, and of course many other people had been doing not too dissimilar things, but you really put the focus on these things, and fortunately that was when I was getting my PhD with him, and here I am, however many years later. But just as a point, a special case, or an example before I do anything, we talked about the Green's function. Let me call it G of Z and Z tilde. The Newtonian potential looks like 1 over mod Z minus Z tilde to the n minus 2, right? That is clearly a function on M cross M, or Rn cross Rn, which is smooth away from the diagonal, and it has a pretty nice singularity at the origin. I mean, it's singular at the diagonal, but in a very sort of nice sense. Okay, so basically pseudodifferential operators are things that are going to be like this. They have some sort of singularity when Z and Z tilde come together at the diagonal, and they're smooth elsewise. Okay, so first of all, what about the smooth elsewise business? So I take this integral. This is sort of defining the Schwartz kernel. So this is the Schwartz kernel, just as I did right up here. This is the case of A. How do I make sense of this? Well, I do exactly the justification I did last time, which, as I said, I take 1 over, let's say, Zj minus Zj tilde d zeta j, applied to e to the I, z minus z tilde dot zeta is equal to, so every time it brings down a this thing, this is going to be e to the I z minus z tilde dot zeta. Okay. Right, so I have this thing is equal to that. Okay, so if I take the sum over j, I'm going to have n times this. So this is going to be just some constant times this. Okay, or I can take coefficients of these or whatever. So the point being now that I can take this thing. Now this thing is has a perfectly good non-zero sense when z is not equal to z tilde, namely when I'm away from the diagonal. Okay, so in other words, all I'm going to do is I'm going to say I'm going to take this integral. I'm going to take 25 of these guys, or however many it takes. So I'm going to take some huge number of these guys, integrate by parts. So namely, this thing is going to equal e to the I z minus z tilde dot zeta. And then I'm going to have, let's say, 1 over z minus z zj, and then just write it figuratively like this, times d zeta j, let's say to some huge power n, a of z z tilde zeta. D zeta. Okay, so again, that's a definition of what this thing is. It doesn't matter how big n is as long as this thing is convergent, because any two such things are equivalent. Okay, and as long as I'm away from the diagonal, so again, you have to mess around, but you choose some region where this particular coordinate choice is non-zero. Okay, as long as I'm away from the diagonal, I can always choose a j so that this makes sense. And the point is that if I differentiate the symbol n times, it gets fast decaying. This becomes convergent. Okay, so in other words, this becomes a perfectly smooth function, but it only makes sense as long as z is not equal to z tilde. So this is exactly the sense in which the Schwartz kernel is smooth, but only when this computation makes sense, which is away from the diagonal. Okay, so this is C infinity away from diagonal. Okay, so now let me tell you what conormal distributions are. And I'm going to do this in stages. Okay, so the first thing I'm going to do is I'm going to take Rn, and I'm going to take the origin. Okay, and I'm going to tell you what the distribution on Rn, which is conormal at the origin, is equal to. Okay, now let's just take distributions, so it's compactly supported distributions. I don't care what's happening outside of the compact set. So I take a u and p prime. We say that u is, so here's the notation of curly a of Rn with respect to the origin. This means, so in words, it has stable regularity with respect to a certain restricted set of vector fields. So what this means here is that u lies in some function space. Take your favorite function space. It can be L2, it can be L infinity, it can be whatever weird function space you choose. So let me just emphasize that. This is equal to some weird function space. But it's fixed. So u is in this, and then I differentiate it as many times as I want with respect to the following vector fields. I take zi d by dzj. So I take the collection of all these vector fields. Okay, the important thing is that they vanish at the origin. These are in fact all vector fields which are smooth on Rn which vanish at the origin. Okay? Or just say any smooth function which vanishes at the origin, any smooth vector field which vanishes at the origin can be written as a sum of these guys with smooth coefficients. Okay, so this is a generating set over C infinity. And so the definition is that any number of these, so let me just write this as z to the alpha, dz to the beta of u, stays in that same function space for all mod alpha is equal to mod beta. So namely, if I differentiate 500 times, but I have to multiply by a monomial of order 500. So I have to hit it with something that vanishes in exactly the same order. That thing is going to lie in exactly the same function space. Okay? And that's the key to being conormal. That's the definition. Okay, so this is sort of centered on these vector fields. So these vector fields are the things which vanish at this submanifold, which in this case is just the origin. So just as a small example, so suppose I take a function that looks like x to the gamma. Gamma can be any complex number. So I take any x to the gamma. Let's suppose we're on the line. Here's the origin. I take x plus to the gamma, so it's 0, and then it can be blowing up at the origin or decaying or whatever. Okay? Well, this x to the gamma clearly lies in some function space. Okay? And when I differentiate it with respect to x, so if I take x dx of x to the gamma, I just get gamma times x to the gamma again. So that's an example of something that doesn't get worse when I differentiate it. Of course, it gets worse if I just take d by dx of it. But if I take x d by dx of it, it stays the same up to a constant multiple. Okay. There are lots of other functions which do this. So just to sort of point out, okay, so give me 2 minutes and I'll get back to that. Yes. So give me 2 minutes. Okay, so So here are some other examples. Well, if I take, let's say, log of x, if I take x dx of log of x, d by dx gives me 1 over x, that's going to be 1, that's not worse. Stays the same. Suppose I take 1 over log of x, and I take x dx of that. I'm going to get, so 1 over x times 1 over log x squared, this is going to be 1 over log of x squared. This is not worse, this is a little bit better. Okay, again, I'm localizing this b in a compact set. So namely, I've described to you a bunch of different functions. They have the property that when I differentiate them with respect to this vector field 5,000 times, they don't get worse. And that's what a conormal thing is. Okay. So there's a big world of conormal distributions. And so that's what it means to be conormal on our end with respect to the origin. Okay, now suppose I have a manifold and a submanifold. So I have S inside of M, it's an embedded submanifold. I'm going to talk about the space of conormal distributions on M relative to the submanifold S. And it's going to be defined via stable regularity once again. It's going to be exactly the same definition, but I have to tell you what vector fields I'm going to use. Okay, so the only choice in there, the only special thing here was I said, I have a particular set of vector fields, and I have distributions which lie in a space, and I differentiate them as many times as I want with respect to those restricted set of vector fields, and they stay the same. They stay with the same regularity class. So I just have to tell you what vector fields to use, and I'm going to define V of M sub S is equal to the set of all C infinity vector fields on M, which are tangent to S. Okay, so away from S, they can be anything, but when I'm along S, they're tangent to it. Okay, so that's a restricted set of vector fields. They're arbitrary away from S, but along S, they have to be tangent to it. This then is equal to the set of U's which are in some, let's be specific about function spaces. Now let's suppose it's in L2 such that V1 through Vn of U stays in L2 for all n and for all of these Vj's in this script V of n and S. Okay, so it says I'm in L2 and I differentiate it as many times as I like, but with respect to these very special vector fields, and I stay in L2. Okay, now let's look in a special coordinate system where S is equal to, so let's suppose that I have Z is equal to Z primed, Z double primed, and here's S is equal to the space where Z double primed is equal to 0. So here's Z double primed, and here's the Z primed axis. Okay, so I can think of U as a function of Z primed and Z double primed. And what are the vector fields that are tangent to S? Well, again, I can write them out like I did here. So if I take any, so let's suppose that Z prime is equal to Z1 through ZK, and Z double prime is equal to ZK plus 1 through Zn. Oops. Okay, so the first K coordinates are these guys, and K plus 1 through N is these guys, right? So then what are the vector fields I'm interested in? Well, I can take any combination to Z prime. So I can take DZI, DZ1 through DZK, okay? And then I can take the ZI d by DZJ for I and j greater than k. So namely, in these directions, I just have a submanifold in the origin, right? So it's exactly the previous case. Okay, so in other words, the space, this V of M and S, is spanned by any vector field in the horizontal direction, but these special guys in the vertical direction. Okay. So finally, here's the definition. So A is a pseudodifferential operator on a space M, if and only if. This is a definition, right? The Schwartz kernel of A is conormal on M cross M with respect to the diagonal. That's it. That's the coordinate free definition. Okay, that's all a pseudodifferential operator is. Okay, so what I have to do for you is tell you why this is the same as this god-awful oscillatory integral definition I made up. But this is sort of a very nice clean definition, and this is the one that we're going to generalize to other geometries. So where I'm really headed, so I spent, a day and a half getting there, is getting to this definition because this is a thing that I can geometrize widely. Okay, everybody happy with this? Yeah.
And it doesn't matter what function space you choose.
Yeah, so in some sense, I can choose any function space and I get some particular space. If I, suppose I put H5 here instead of L2, right? Well, then that would have just said that, it's the same function space because saying that you lie in H5 away from the diagonal, you're differentiating as many times as you want, you stay in H5, it means you're smooth, right? So it gives you a slightly different singularity. So so anyway, I can sort of take a scale of function spaces here. So I can take HS as S varies from minus infinity to plus infinity, and those give me a filtration of A. So namely, A itself breaks up into pieces of regularity, which is how regular you are along the diagonal. It sort of depends on which function space you choose there. That's exactly right. So finally, to answer Alice's question, if K sub A of Z and Z tilde is equal to Z minus Z tilde to the 2 minus n, okay, this clearly has this property. So namely, here's Z Z tilde, so the diagonal is that thing right there. Away from the diagonal, this is perfectly smooth. And then what are the vector fields? I'm interested in their tangent to the diagonal, and they sort of have this linear growth away from the diagonal. Okay. Why is this okay? Well, if I differentiate this thing tangent to the diagonal, it's constant. So it's clearly smooth. On the other hand, if I differentiate in this direction, well, it's an easy exercise to say the singularity stays the same. It stays blowing up like, distance to 2 minus n. Okay, so this looks like, distance to the diagonal to the 2 minus n. I differentiate with respect to anything which is, has this form, and it stays bounded by distance to the 2 minus n. Okay, any questions about that? Yeah, Steve.
Sorry, one more question.
Sure.
You wrote psi x for the actual weight of the n before.
So in fact, that's exactly right. If I filter A, if I choose a whole scale of regularity for A, namely depending on what function spaces I choose to be along the diagonal, then that corresponds to filtration of that thing. And I'm going to tell you a very special filtration. Namely, how do I sort of, measure regularity along the diagonal? And the problem is, it's not L2. It actually corresponds to L2 in a weird way, which you'll see in just a moment. Okay, is everybody good with this definition? Okay, so to now relate, so I have to spend a few moments relating this to our previous definition of pseudodifferential operators. Why is this giving us the same thing? And so I can do this in 2 stages. One is saying that, the Schwartz kernels I wrote down have this property. And the second is that, we'll see. Okay, so first remember that K sub A of Z and Z tilde. So I'm going to write it now in the following form. I'm going to write it as, let's say, K sub A tilde, so I'm just a linear change of variables, of Z plus Z tilde and Z minus Z tilde. Okay, so all I'm doing is just rotating coordinates. Okay, and so let me call this K sub A tilde of W and W tilde. Okay, so all I've done is I've taken this picture and I've reduced it to this picture. So W tilde is equal to 0 is the diagonal now. So there's the diagonal here, so I don't use color chalk. But there's the diagonal, it's gone to this thing here. Okay? So what are the good vector fields here? Well, I can take any d by dw's, right? And then I can take the wi tilde dwj tildes. Okay, now remember what this oscillatory integral definition is. E to the I z minus e tilde, that's w tilde. Right? Times A, now I'm going to write A as a function of W tilde, and zeta d zeta. There's the Schwartz kernel. I've just rewritten in the W and W tilde coordinates. Okay. And so now I have to check that this is a stable regularity. So this is a distribution of some order. You know, I take zeta, I take the, you know, distributional meaning, you know, I take this sort of regularized thing, it gives me a distribution of some order, whatever it is. Okay, and when I differentiate with respect to w, it doesn't hit this exponential here. So any w derivative is fine. This a is supposed to be smooth in w, so I can differentiate as many times as I want there and it doesn't get worse. Okay, so that means like differentiating like this or differentiating like this. Okay, on the other hand, if I take w tilde derivatives, if I hit there, that's fine. But if I hit here, what goes wrong? Well, suppose I take a wi tilde dwj tilde, acting on e to the I w tilde dot zeta. Well, the dwj tilde is going to bring me down to zeta j, and the wi tilde is going to be like a d zeta I. Okay? So dwj tilde brings me down to zeta j, wi tilde, well, excuse me, so let me just say, what do I want to say? I guess that's right. So if I take a d, well, let me see. Maybe I want to put these in the other order. Zeta j d zeta I. D zeta I. Because if I take a d zeta I, it brings me down to w dot I tilde, and zeta j corresponds to bringing down it. Zeta j corresponds to differentiating with respect to wj tilde. Okay, so in other words, in this integral, I can just say, well, this is the same as taking this thing. So it's like, so if I differentiate this with respect to these guys, so if I take, if I take a wi tilde dwj tilde of this e to the I w tilde dot zeta times a, this is the same as inside the integral, taking a zeta j d zeta I of e to the I w tilde dot zeta times a, integrate by parts, e to the I w tilde dot zeta, and then I'm going to have a d zeta I times zeta j times a of w tilde zeta. Zeta. So again, this is all formal, but I make sense of it in terms of these, you know, regularized oscillatory units. Okay, so I've applied a single vanishing vector field to this Schwarz kernel. I rewrite it this way. I integrate by parts, and what do I have here? Well, remember, A was a symbol of order m. If I multiply it by a monomial, it's a symbol of order m plus 1, and then I differentiate it, it becomes a symbol of order m. So namely, this is exactly, so this whole thing is a symbol of order n. So in other words, hitting it with this thing gives me a new oscillatory integral with a symbol of exactly the same order. And that's why it doesn't get worse. But why you need this extra factor here. So if I didn't have that extra factor, I'd be in trouble.
Does this change of variable correspond to the original thing on diagonal?
Well, so this change variable here,
Yes.
all it corresponds to is taking the diagonal and making it horizontal. Okay, so in other words, what I've justified is that this expression, which I've written down, is conormal with respect to the diagonal. It's a distribution of some order, and I differentiate it with respect to these guys 3,000 times, and it's a distribution of exactly the same order. Okay, where do symbols fit in? Well, I've talked about symbols here. I want to go the other way. So what I've done is I've said, given a symbol, I've defined an operator via this prescription, and that operator, or that Schwarz kernel, is conormal. I'd like to go the other way around. Suppose I have a conormal distribution, a la this definition. Suppose I take an arbitrary conormal distribution. I need to produce a symbol for you. All right, so I started with a symbol, got a conormal distribution. That was this calculation. I want to go the other way around. Given a conormal distribution, I want to go get a symbol. So conormal distribution. So I want to go conormal distribution to symbols. How do I define that? Okay, so I'm going to use some of these calculations here. So suppose I have a conormal distribution, k sub a of z and z tilde. First step is I turn it into this k sub a tilde of W and W tilde. So all I'm doing is I'm flattening out the diagonal. So it's this step here. So I have something conormal here, I turn it into something conormal here. So now I have something which is conormal with respect to this subspace here. Where am I going to get a symbol? So what I do is I Fourier transform normal to S. So here's S, right? Here's this special submanifold. If I take the Fourier transform transverse to S, I'm going to get something. So namely, what I want to do is I want to take K sub A of W and W tilde times e to the minus I W tilde dot zeta, dW tilde. And the claim is that's a symbol. Okay. So in other words, the correspondence is, given a conormal distribution, I Fourier transform normal, perpendicular, transverse to the diagonal, I get a symbol. If I have a symbol, I insert it into this oscillatory integral and I get a conormal distribution. That's the correspondence. Now, why is this a symbol? Why is this a symbol? Well, clearly it depends on W, sort of this is smooth, you know, what's happening in W is perfectly smooth. You can forget about that, that's like a parameter. Right, so the dependence on W is just a completely smooth parametric dependence. And so the only interesting thing is what happens in W tilde. So I can forget about W for the moment. And I'm just going to reduce to sort of being an Rn. So here's the W space, the W tilde space. So here's Rn. This is variable W tilde. Here's W tilde is equal to 0. And I have this function K sub A tilde of W tilde. I forget about the W dependence because it's smooth. Okay. I take the Fourier, and I suppose that I'm supported in some wall, so I don't care about what's happening outside here. I take the Fourier transform. This is some function which I'm going to call A of zeta. So why is this a symbol? Okay. Well, in words, it's something that you have known forever, which is that Fourier transform takes growth at infinity to smoothness, and it takes smoothness to growth at infinity. It interchanges smoothness and growth at infinity. That's really exactly this computation here. The Wi goes to d zeta j, and dwj goes to zeta i. Okay? So in other words, we need to show that this is a symbol, and it's exactly the same computation I did there. So suppose I take a zeta I d zeta j of A. Right? So if A is supposed to be a symbol, d zeta j makes it one order better. Right? And then multiplying by zeta I makes it the same. Right? So symbols have the property. So I could have either said what I originally told you, which is that differentiating 5 times gives you something that's 5 orders better. Or if I differentiate with respect to these vector fields where zeta is going to infinity, these vector fields I differentiate and then I multiply by a monomial. These stay the same. Right? So A is an SM. This would be an SM minus 1. This goes back to SM. Okay. Well, so the point is zeta I d zeta j of A is, well, it's exactly the same computation. This is going to be e to the I w zeta, and then there's going to be a dw I times w j tilde of K sub A. So namely, I put this derivative on the exponential, I bring it over to the other term by integration by parts, and I get this, and the whole definition of conormality was this didn't get worse. So I'm taking the Fourier transform of something that's exactly the same. Still an L2 or whatever it is. Okay, so in other words, the fact that I'm conormal means that this is operative near W equals 0, W tilde equals 0. This is not getting worse when they differentiate with respect to these guys near W tilde equals 0. That's the same as this thing not getting worse when they differentiate with respect to these guys near zeta equals infinity. So Fourier transform interchanges growth in regularity near 0 versus growth in regularity near infinity. And it's this computation. Okay, so that's kind of one of the key points of all of these lectures, is that symbols, which had this nice definition, but kind of got this very technical sort of integral thing, correspond exactly to these guys.
using the order of m.
Okay, so where does the order of m come from? If I have, so this is now my filtration. If I have a symbol of order m, then this is supposed to come to some sort of function space on the conormal distribution. So in other words, psi sub m, the operators I'm interested in, correspond to symbols of order m. Namely, if I put in a symbol of order m, I take this, wherever the integral went, this integral, e to the I, z minus z tilde dot zeta, a of z tilde zeta, d zeta. If this is bounded by 1 plus mod zeta to the m, whatever m is, that's going to give me a certain distributional order at z equals z tilde, right? And that's the filtration. It's an L infinity bound on one side of the Fourier transform, gives you some horrible bound on the other side, right? L infinity doesn't sort of transform that. Well, it transforms nicely in terms of S on spaces. So if I were using L2 here, if I said that A lay in some weighted L2 space as zeta goes to infinity, that would correspond to this thing, if little a lying in some weighted L2 space near infinity, that would correspond to K sub A having some weighted L2 regularity near zero. But I've chosen an L infinity weight near infinity, so it gives me some other weird, strange way of measuring regularity near zero. Okay. Okay, so this definition is a very flexible definition now, and I hope this justifies exactly what I said. This is kind of a clean statement here, just geometry or differential topology or something, right? This is just saying I have a manifold, a submanifold of conormal distributions. Think of those things as Schwartz kernels, proof that's it. Okay. Where does all the meat lie? Well, if I want to do anything with these guys, I have to write them in coordinates. Namely, I have to write these things as oscillatory integrals via this Fourier transform. Okay, so in other words, this is a nice definition, but the things that you want to prove. So you want to prove, and we talked about how to do this yesterday. Want to prove composition and boundedness on L2, etc. So composition is A composed with B is again something of the same sort. So if I have two operators which satisfy this conormality property, if I take the composition, so if I take K sub A of Z with Z primed times K sub B of Z primed with Z double primed, dZ primed, this is equal to the Schwartz kernel A composed with B of Z and Z double primed. It's just sort of a formal thing. This is how you compose integral kernels. If K sub A and K sub B are conormal with respect to the diagonal, it's not at all obvious that this thing is conormal with respect to Z equals Z tilde. Right? So you have to prove that. And that you prove via, well, all the mess I talked about yesterday. Okay. Okay, so now I'm going to start talking about material that's closer to what Alice talked about yesterday. But before I do that, I want to give a very small, and it was something that she mentioned and I want to sort of justify. And it's very related to the thing I said at the very end of the lecture yesterday, which is, remember, if M is a compact manifold, I have a Riemannian metric. I can define Laplacian sub G, and I can take the powers of Laplacian sub G. Okay? Now, how do we make sense of this? There's several ways to make sense of this. One is just via the functional calculus, right? This is a self-adjoint operator, it has a discrete spectrum. I take the eigenvalues to the power S. Okay? The statement that I proved, so this was Seeley's theorem, is that this is a pseudodifferential operator of order 2s on M. Okay, so what's interesting about this theorem is not that I can define this, because I have 5 other ways to define the fractional Laplacian. What's interesting is that it's a pseudodifferential operator. Why is that interesting? Because, well, think about it. If I define the Laplacian to the S via L2 spectral methods, for example, okay, so if I define this via the functional calculus, I know what it is as an operator in L2, right? In case that's the case, I'm down to operator in L2. And then suppose that I hang around some street corner and somebody asks me, how do I define this as an operator on Holder spaces? Is that true? How do you prove something like that? Well, if you have the spectral definition, you're up the creek, right? You have no idea how to do it. Or you have to work very hard. But Seeley's theorem tells you a very good way to do it. It says it's a pseudodifferential operator. Any pseudodifferential operator has this property, so voila, that's it. So having this concrete description of what this thing looks like, Schwarz kernel and whatnot, tells you a whole bunch of other stuff about it that you don't have to derive specially for this particular operator. You have all the rich properties of pseudodifferential operators to tell you. Okay. This might have some special properties amongst them, and those are things we're interested in, but it has a whole bunch of general properties like boundedness in various function spaces. So the moral of that is that if you have an operator that you care about deeply for some other reason, it's very useful to identify it as a pseudodifferential operator. So that's why we do it, because it's a very helpful description. If you want to study that operator in a flexible way, as I talked about yesterday, it's really nice to have a description of it as a pseudodifferential operator. So let me give you a small extra application of this before I go on. And so Alice talked about the following thing. Suppose I have a bounded domain, smooth bounded domain. And I talked about, and I look at the Dirichlet-de-Neumann operator. So let me give you a careful statement of what that theorem is. Okay, so let's suppose that I have a domain, omega, inside of Rn or a manifold. Let me just say inside of a manifold. It's a smooth bounded domain. And I'm going to take the operator, I'm going to call it d sub g. This is equal to the Dirichlet-de-Neumann operator. And remember how it's defined? If I take a phi on the boundary, suppose I take a phi, which is, well, it can be a distribution on the boundary of omega. I solve Laplacian sub g of u equals 0 in omega. U restricted to the boundary of omega is equal to phi. There's ways to make sense of this even when phi is a distribution. So it's fine if phi is, but if it's a smooth function or an L infinity function, that's fine too. Okay, so you can always make sense of this. You can always solve this. Okay. So the Dirichlet-de-Neumann operator applied to phi is exactly the normal derivative of u at the boundary of omega. Here's omega, whatever it is. I find u in the interior, and then I take this normal derivative. Okay? And so here's the theorem. So there's a whole bunch of abstract theorems which tell you, you can do this by energy methods. I mean, Alice described this briefly yesterday. You can make sense of this, and in fact, you can make sense of it for Lipschitz domains, and it's a very flexible thing. The theorem is that if omega is smooth, so the boundary is smooth, then d sub g is a pseudodifferential operator of order 1. So I've identified it as a concrete operator, and I'm going to do one better. I'm going to say that its principal symbol, sigma sub 1 of d sub g, this is a function of y and eta. So if here I have variables, so here x is normal to the boundary, y is tangent to the boundary, and eta is the dual Fourier transform to y. This is equal to mod eta with respect to g. So namely, I take the Fourier transform variable, take its norm with respect to the metric g on the boundary. Okay, so that's a completely concrete description of this operator. In fact, there's more. You can say that d sub g is a pseudodifferential operator of order 1. Here's its principal symbol. That's a very clean statement. You can write down its entire symbol. So there's an entire symbol expansion for d sub g, for sigma of d sub g. It has a bunch of lower order terms. Right? And in fact, so this is a beautiful theorem of Jack Lee and Gunther Ullmann in about 1992, something like that, I don't know, which said that the complete symbol of d sub g determines and is determined by the Taylor series of the metric at the boundary of omega. So in other words, I could write down all the lower order terms. Remember I talked about symbol expansions yesterday? So if I write down all the lower order terms of the symbol expansion, I can recover the entire Taylor series of the metric from that. And vice versa, the Taylor series of the metric tells me what the entire symbol expansion is. Okay, so this is a theorem of exactly the same sort. Now, let me just sketch the proof of, well, the first part. I'm not going to talk about this. Let me sketch the proof of this first part because it's a really lovely application of this. This shows you how flexible pseudodifferential operators are. Okay, so how do I write the Laplacian? Well, if I were in Euclidean space, this would look like, so let me flatten out coordinates. Here's x, here's the y direction, and there's going to be some metric h on the boundary. Okay, so this is going to look like d by dx squared plus Laplacians of h, right? If I were in a product metric. But since I'm not in a product metric, there's the first order term. So this is using Fermi coordinates. If I exponentiate off of a boundary, then there's no cross terms here, but there's a first order term, which involves the mean curvature of the boundary and blah, 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 stuff like that, okay? So this is an expression for the Laplacian. Okay, so now here's the great thing you can do with pseudodifferential operators. I'm going to rewrite this as d by dx plus I times the square root of minus Laplacian times d by dx minus I square root of minus Laplacian plus v. Okay, these all make sense as pseudodifferential operators. And of course, once I do this, I make some smooth error terms, so let me add in one of these smoothing operators. Okay, so I can factorize. So now what am I really doing here? I take the symbol c squared plus mod eta g squared. That's the principal symbol of this guy. And I'm rewriting it as c plus I mod eta times c minus I mod eta. So these are two symbols. Once again, I have to stay away from the origin. But again, it just adds the smoothing error. So I just factorize this algebraic thing, which is easy. I know how to factorize polynomials. But of course, these things aren't polynomials anymore, but they're symbols. So I quantize the symbols, and there they are. That's what the quantization of those symbols is. Okay, how does that help me? And how does it prove this theorem? So it's a very cool proof because it gives this to you in a very direct way once you've done this. Okay, so what does it do? So remember, I have this Laplacian sub g of little u is equal to 0. And I'm interested in calculating the normal derivative of u at the boundary, x equals 0. So I rewrite this as d by dx plus I squared root of minus Laplacian sub h times d by dx minus I squared root of Laplacian sub h applied to u. And that's going to equal minus v of u minus the smoothing term. That's just the statement of the fact that Laplacian is harmonic. I have this equation. Okay? The h is the boundary Laplacian. That's exactly right. Okay, so everybody agree? I've done that. Now here's the other beautiful thing that happens. This guy is elliptic. Right? What's its symbol? It's I times c plus mod eta. I probably screwed up factors of I, but believe me, this one's elliptic or the other one's elliptic. Let's suppose that this one's elliptic, right? Okay, good exercise for you to check. So this guy's elliptic. There's its symbol. It grows linearly in c and eta, and it's elliptic because I have this I here. Okay, so I probably screwed up. Anyway, I'll leave that to you to figure out. So this guy's elliptic. What can I do with elliptic operators? I can invert them. So I can rewrite this equation as d by dx minus I squared root of minus Laplacian sub h of u is equal to whatever the inverse of this guy is. So let me call it g of minus v plus r of u. So this g is an inverse of parametrics for this d by dx plus I root minus Laplacian. Okay, so of course I can invert it up to a compact error. So that's some other smoothing operator. Okay, every time I sort of do one of these formal operations in the level of symbol, at the level of operators, I get some smooth jump terms. Okay. Well, this is exactly what I wanted, because look what this says. It says d by dx of u is equal to I times the square root of minus Laplacian sub h of u, plus all of these terms. Well, let's think about what these terms are. V is of order 1. V is a vector field. G is an inverse to a first order elliptic pseudodifferential operator. So that's of order -1. So that's of order -1, that's of order +1. And so all I'm going to get is this plus some junk term, which I've used up QRS, I don't know. So T of U, where T is a pseudodifferential operator of order 0. Okay, so let's just review what I did. I said I took the equation, I factorized the symbol, I turned that into a factorization of the operator, but now it's a pseudodifferential factorization instead of a differential factorization. I rewrote the harmonicity condition like this. I always have a bunch of junk terms, these smoothing operators that I get from quantization, and this tells me this. And this is exactly what I wanted. It says the Dirichlet-Neumann operator, d by dx of u, is exactly this guy, is a first order pseudodifferential operator, plus something of low order. And that's the theorem. So I've explicitly identified the Dirichlet-Neumann operator as a pseudodifferential operator, and there's its leading part. Okay, so this really is why pseudodifferential operators are so great. You can do everything you can with smooth functions with them, essentially, if you're careful.
I have a question about this Neumann theory.
About what?
The complete symbol of this Dirichlet Neumann is determined by the G on boundary.
Yeah.
I thought it also depends on the extension.
Okay, so in fact, no, it does. So this is an important point. So the complete symbol, like the Taylor series of the symbol, if you like, is determined by the Taylor series of metric. The complete operator is the complete symbol plus some smoothing term. So that's actually what's very important. The Dirichlet-Neumann operator has this purely symbolic part. All the symbols of order 1, 0, -1, and so on. Those are local at the boundary. Plus some global smoothing term. And that's the guy that depends on all the geometry in the interior. So all these inverse problems, I mean, so what Lee and Ullmann were doing, for example, was trying to study this inverse conductivity problem. If you know the Dirichlet-Neumann operator on the boundary, what can you say about the interior? Right? And that's in this anisotropic case, in this general metric case, this is a really hard problem. It's still unsolved in general. This is smoothing. This Q is smoothing. And this R is smoothing too. So you have these global smoothing terms that you have no control over from this argument. All this tells you about is, so what pseudodifferential operators are great at telling you about is like Taylor series extensions, you know, kind of these formal calculations. But it reduces everything to then you have some global smoothing that they have to worry about. Okay. Any other questions about this? Yeah.
So you said V is some cross term that you get, so you could
It's a first order term.
You could kind of compute the subprinciple symbol using this as well.
Yeah. So I mean that's what Lee and Ullmann do.
Okay.
They just sort of keep on cranking the handle. That's exactly right. In other words, they just do this kind of computation much more carefully.
Yeah.
Okay, so now we're at the point where on a compact manifold we know everything about pseudodifferential operators. Well, we can derive it from what I said. Okay, so now what if M is an open manifold? Okay, well I told you that I can always define psi star of M equals the set of A such that K sub A is conormal on M cross M with respect to the diagonal. That's always true. That's always a definition. However, when M is an open manifold, this doesn't tell you very much beyond what's happening right at the diagonal. Okay, so let me give you an explicit example of this, which is closely related to what Alice was talking about yesterday. I'm going to take MG to be conformally compact. So I'll remind you what that is. And the test case, special case, hyperbolic space with its hyperbolic metric. Okay, so I think the hyperbolic space is the ball. And what's the nice feature about the ball? Well, it's a metric that's nice and smooth in the interior, but at the boundary of the ball, this is the Poincare model, it blows up. So what is the hyperbolic metric on the ball? It looks like dz squared over 1 minus mod z squared squared. I guess there's a factor of 4 here to get the curvature minus 1. Okay, this function, 2 over 1 minus mod z squared, is a smooth function on the ball. I'm going to call this 1 over rho, which is equal to 1 minus mod z squared over 2. This is C infinity of the ball, the closed ball, and rho equals 0 on the boundary of the ball, and d rho is not equal to 0. So in other words, I take this function which vanishes on the boundary of the ball, and it's a defining function, and this just looks like the Euclidean metric divided by rho squared. Okay? And so the definition that Alice gave of a conformally compact metric says I replace the ball with any compact manifold of boundary. So I take any compact manifold of boundary, M bar, I take a defining function for the boundary, rho, and I take a metric G bar on M bar, so there's some nice smooth Riemannian metric up to the boundary, non-degenerate up to the boundary, and divide by rho squared. And that's what a conformally compact metric is. So all I've done is kind of mimic what this is, namely I've taken a nice smooth metric up to the boundary and then blown the boundary out to infinity conformally. Okay, and you can do a very easy computation. So this guy is complete. That's because there's 1 over rho squared. So when I integrate, I'm integrating one, if I take the lengths of geodesics, they're infinite. And so this is complete, and this guy has constant negative curvature. These guys, their curvature is whatever the hell they are in the interior. So it has variable curvature in the interior, but as I go to the boundary, the curvature is going towards -1. I have a small condition on the one jet of rho of the boundary. So the curvature, the sectional curvatures go to -1 of the boundary. Okay, so that's what a conformally compact metric is. So the question then is, suppose I take my favorite operator on hyperbolic space or on the ball or on a conformally compact manifold, and I try to understand this Green's function. So for the moment, my favorite operator is just the Laplacian. It'll change in a moment. But suppose I take the Laplacian with respect to this conformally compact metric. So here we are. Here is this mg, conformally compact. I have this Laplacian, and I'd like to understand what is its Green's function. Okay. So what do I know about this Green's function? So again, this is going to be an exercise in the same sort of thing. There is a nice L2 spectral theory, which you can do, which just involves integration by parts, very elementary argument, which says that the L2 spectrum of minus Laplacians of G is equal to the interval from n-1 squared over 4 to infinity. My manifold has dimension n. Okay, so in other words, here's the spectral picture. It's continuous, absolutely continuous spectrum from n-1 squared over 4 to infinity, nothing else. That's at least if I'm on hyperbolic space. If you're not on hyperbolic space, but one of these general conformally compact manifolds, there might be some extra spectrum. There might be some discrete spectrum down here. And in general, from general study of Schrodinger operators, you might expect embedded spectrum too. There might be point spectrum sitting inside the continuum. So it's actually an old theorem of mine that says that there's no embedded spectrum. So in fact, it's just absolutely continuous spectrum from n-1 squared over 4 to infinity, plus a finite number of eigenvalues here. So that's, well, okay. So this tells you that there is a Green's function, right? So this tells me that there exists a G, which is a bounded operator on L2. Just abstractly, just using functional analysis, right? Why is it? Because there's no spectrum right at 0. 0 is spectrally isolated. So I can take the inverse as a bounded operator. Okay, so that's just using abstract functional analysis. There is a Green's function. So, question, just like I did with these other operators, is this a pseudodifferential operator? Okay, so here's the theorem. G is a pseudodifferential operator of order -2, and I'm going to put an embellishment there, which I'll tell you about eventually, but sub-0. Now, what this sub-0 means is it's a different class of pseudodifferential operators. I'm going to tell you what it is. Okay. So this is, again, a concrete identification. Why is this so great? Right? Because then you can do a whole lot of other things with this G. So this abstract definition only told you that G was bounded on L2. This tells you that G is bounded on Triple-Zorkin spaces or whatever the hell you want. Right? I mean, you can get boundedness on any function space you want. You can do a lot of other things with G. besides boundedness, but it's a very flexible description. So identifying it as lying in a particular operator class buys you along. Okay, so what is this psi sub 0? So in some sense, I'm in this great shape. So I don't know, I guess yeah, there we go. So I have this description on an open manifold, conormal distributions. So here's my manifold, here's M cross M, and it goes off to infinity. Here's the diagonal. And at the leading stage, this is exactly right. Near the diagonal. So let's just suppose I cut off to a neighborhood of the diagonal. Suppose I cut off to a neighborhood of the diagonal. This is a pseudodifferential operator here, in the sense that we know and love by now. Okay? So there's a nice conormal singularity along the diagonal. We're really happy with what happens here. Okay? What's the new feature is what happens way off of the diagonal, the far field expansion. So that's kind of the new feature. So this is not a singularity per se. This Green's function is completely smooth, but I want to know it's asymptotic since I go a long ways away from the diagonal. And that's sort of what this 0 tells me in this script E. Okay, so our motto is compactify and conquer. Well, maybe compactify and blow up. So that's how we describe what happens a long ways away from the diagonal. Okay, so what do I mean by these terms here? So the first thing I want to do is I want to take M, so remember here's M, here's M, I want to compactify that picture. Now, if I reduce, so my drawing abilities now shrink from 2 dimensions to 1 dimension. When I compactify a manifold, I get a closed manifold. When I take the product of itself, all I can draw is a square. Here's M bar, here's M bar. Right? There's M bar across M bar. That's my compactification. Okay. Where's the diagonal? It's this guy here. Okay. And what I need to tell you is, well, I know exactly what's happening to along here. I have this pseudodifferential singularity. I have this conormal singularity along here. The question is what's happening at all of these boundaries, and in particular, what's happening at these corners. So that's the new feature. So I'm trying to, my description of this Green's function, the key properties are both what's happening in the diagonal, which is already interesting, but then what's happening in the far field. Notice that these are an infinite distance away. I mean, remember this metric is complete, so when z and z tilde diverge, I'm going an infinite distance away. Okay, and this is very sensitive to the geometry. Now, I could have done this in any complete geometry. So if M was asymptotically Euclidean or asymptotically whatever else, I could have drawn a picture that looked just like this, but the description of what happens near these boundaries would be completely different. Okay, so this is where the geometry becomes very sensitively involved. So I'm using this asymptotically hyperbolic geometry. I'm going to tell you what happens near these points. Okay, everybody happy with that? So I've compactified. I haven't blown anything up yet, but I've compactified. Okay, well, to tell you what happens, I'm going to now revert to upper half space coordinates. So I'm kind of omitting a point at infinity, so I'm slightly different than this picture. So I'm going to think of M bar as being like this. So I have coordinates x and y. And so there's this nice theorem that Alice mentioned yesterday. This is the Graham-Lee normal form. And it says that any conformally compact metric can be written in the form dx squared plus h at linear right explicitly is h of xy dy divided by x squared. So in other words, this is really looking very close to hyperbolic space where this is just the Euclidean metric. So this is a metric on this y slice, but because there's this x dependence, it's sort of a family of metrics on every x equals constant slice. Okay, so these are sort of Fermi coordinates at infinity. Even though it's complete, I can talk about sort of exponentiating off of infinity. I have Fermi coordinates to infinity. Any conformally compact metric can be written in this form. And you get that by solving the Hamilton-Jacobi equation. It's a kind of slick proof. It's not very hard. Okay, so that tells me that I should be looking at this upper half space model. I have a nice way to do computations here. And now, what is so M bar means I'm just including x equals 0. So I have a half space. Okay, M bar cross M bar, I now want to draw symbolically like this. So here's x tilde, here's y and y tilde. So I'm thinking of on the first copy of M, I have coordinates x and y, and on the second copy of M, I have coordinates x tilde and y tilde. here's the die. This is the space where x equals x tilde, y equals y tilde. And what I want to tell you is what's happening near x equals 0, what's happening near x tilde equals 0, and in particular, what's happening along this corner and at where the diagonal hits there. So that's where all the complicated story is. And so here's the basic observation, which sort of tells us what we should be doing, which is that in the exactly hyperbolic case, there's an extra symmetry, or two extra symmetries. So let's say in Hn itself, the metric looks like dx squared plus the Euclidean metric divided by x squared. Here's the same picture, x tilde, y, and y tilde. Now the fact that I have a translation in the y variable, right, that's an isometry, that means that I expect to have a convolution operator in y, which means that it should only depend on y minus y tilde. Remember, I'm looking for Green's functions, and they should be convolution operators in y in this special case. Okay, so I'm expecting to write this, so I could really sort of divide up my coordinates just like I did before, but just on the boundary, y minus y tilde and y plus y tilde. And the point is the y plus y tilde variable in this case is trivial. In general, it's some smooth parametric dependence. Okay, so that's the first thing. The second thing is that the mapping xy to lambda x lambda y is an isometry of Hn. Just dilation from the point at the boundary. It's not, I'd say, a hyperbolic isometry. So what that tells me is that when I sort of dilate this picture, I should have, well, so what it should tell me is if I take Laplacian in the hyperbolic space times the Green's function, so this is acting in z, acting on the Green's function, which I'll write explicitly as x tilde, and y minus y tilde. This is equal to the delta function. Now, let me just say the identity. As a distribution, maybe I'll write it as the delta function. And so here's kind of the point. What's the homogeneity of each of these objects? What's the hyperbolic Laplacian? It looks like x squared d by dx squared plus x squared times Laplacian sub y plus 2 minus n times x dx. That's the Laplacian in hyperbolic space. Okay, the delta function is homogeneous of degree 0 if I think of it as a density. Right? This is homogeneous at degree 0 because x dx is a homogeneous vector field. So this is homogeneous at degree 0, that's homogeneous at degree 0, which means that this has to be homogeneous at degree 0. So what that means, what's the homogeneity here? It means if I look at sort of the dilation, I take all the rays coming into this point, it has to be constant along those rays. So what I'm going to do, I'm going to introduce polar coordinates. So I introduce spherical coordinates. Around the point. So this is the point in the corner, x equals x tilde equals 0, y equals y tilde. Okay, and let me say it more directly, I introduce spherical coordinates and take them seriously. So namely, here I introduce spherical coordinates and I want to add in the r equals 0 face. So this is, so I have, let's say, r, which is equal to the square root of x squared plus x tilde squared plus y minus y tilde squared, and omega, which is equal to x tilde y minus y tilde divided by r. These are spherical coordinates. This lives on the sphere of some dimension, sort of a quarter sphere of some dimension. Here's the radial variable. Here is the r equals 0 face. And I've added it on. So this is the notion of blowing up. So what I've done is I've introduced the r equals 0 face in a singular coordinate system. R is what? So r is sort of, it measures the distance away from this face. And the homogeneity, well, here's the diagonal. This is the diagonal. And what are these sort of curves, these orbits under this dilation? They correspond to sort of different rays which come into this space. And what the space does is it separates out these different directions of approach. Okay. So what I've done is I've introduced a new space. And I'm going to call this m cross sub 0 m, or sometimes m sub 2 0. So this is a blow up of m cross n. So now there's a whole category of objects. If I have manifolds of boundary, I can do the following operations on them. I can take products of manifolds of boundary themselves. I get corners. I can take more products of those. I get more higher co-dimension corners and so on. So that's sort of one set of operations. And another thing is if I take a nice submanifold to the manifold of corner, I can blow them up, which means I introduce polar coordinates and put the r equals 0 face in. That gives me a new manifold of corners. So these are all kind of categorical operations in the category of manifolds of corners. So there's a whole set of things that you can do. And so what I've done is I've said, take m cross m, compactify it, and then blow up this submanifold in the corner. And that gives me a new manifold of corners, which I'm calling m sub 2 0. And then here's the definition, is that psi 0 star of m, so the good space of pseudodifferential operators on this thing, is equal to the space of operators A, such that K sub A is conormal on M2 0 with respect to the diagonal and the boundaries. So let me translate that into English. What does that say? It says that I have Schwartz kernels which live on this space instead of just this space. Okay? Well, it's fine. Anything does. I blow it up, it stays a distribution. So that's not saying anything. To say that it's conormal on this space around the diagonal and this thing is telling me something very special. It says this Schwartz kernel has the property that, well, in the model case, it was homogeneous to degree 0. In general, it has some sort of expansion as I go towards the front face. It has like a Taylor series at the front face. That's a type of conormality. It has a Taylor series as I go to the diagonal, as I go to the side faces, and it has sort of a standard Green's function type singularity along the diagonal. And everything is completely uniform along here. So there's no degeneration along this face here. Okay, so what this now tells me is that on this sort of more complicated space, I have something which is incredibly well behaved. It's smooth away from the boundaries in the diagonal. And at these various boundaries, it has Taylor series, or kind of more generalized Taylor series expansions. So this is a nice description. Why is this a nice description? Because anything that has a Taylor series, you can solve the terms of the Taylor series inductively. Right? So just think, if you have a C infinity function, you want to know about it, in the middle of a region where it's smooth, it's just smooth. It's featureless. Right? But at the boundary, you can calculate its Taylor series. And that's exactly what this E, where did the E go? There it is. That E, that just tells you what's the exponents in the expansion as I go to these spaces. Okay? So this is now a complete description of the Green's function on this space here. Okay, so let me finish with one sentence, and I'll pick this up on Thursday, I guess, is the next lecture. And let me just tell you where I'm going in the next 2 lectures, because we've talked about fractional Laplacians, but not what I sort of announced in my abstract. So the first thing I want to get to is, if I don't do this to the Laplacian, but for Laplacian times s times n minus 1 minus s, inverse, the so-called resolvent of s. This has a description like this, which has some extra features. So I'll tell you a little bit about that. Okay, so that's one thing, is I want to talk about this as an element of this pseudodifferential calculus, and what this extra description tells you, and it's very closely related to Alice's talk yesterday. The second thing I want to talk about is what's now called as the cover-LA. So that's for extension for the fractional Laplacian. This is just this in disguise, or rather, this is just this in a flat case, essentially. So this is kind of a very special case of this story. And this story was known in 1986. This is from 2006. But regardless, it says if I wanted to find the fractional Laplacian on Rn, I look at an extended problem I'm going to call L sub s. And this L sub s has exactly the same sort of degeneracy as this guy here. So it's going to have this vanishing coefficients at the boundary. Okay, so this Caffarelli-Silvestri extension operator has the same kind of degeneracy as the hyperbolic Laplacian. So all of this machinery can be used to study it. Okay, so I'll review that. And then the final story, and this is what I'll get to by Friday, is suppose I have a smoothly bounded domain. And I want to take a function, let's call it little u in here, let's say 0 out here, and I want to define minus Laplacian to ds of u. So I take a function which is u here, 0 out here. And so what does the extension method tell me? It says I have to use this as boundary data for some function up here. I study this operator in Green's function, everything using all these differential techniques. And then I take their Neumann derivatives down on the boundary. That's the fractional Laplacian. What's happening near the boundary? So that's the new feature. So there's now an added singularity. So I not only have the singularity as this variable, upper half space variable goes to 0, I have the singularity at the interface. Okay, and this is actually a generalization of the classical Zaremba problem. Where a Zaremba problem is like I have a domain and I specify Dirichlet conditions on one half of the domain and Neumann conditions on the other. So this is very much like this. And so in fact, there's sort of a complete regularity theory, what's happening near this interface, but it's sort of a two-step regularity theory. It's what I call the iterated edge calculus, because I have sort of the degeneracy as I go down here, and I have a new degeneracy as I go down towards this face, and I have to blow up more times. Okay, so I'll stop there. Any questions? Yeah.
Your discussion earlier that you said in the
Yeah.
how does it deal with fullness?
I can do your thesis for you. That's for you to discover.